Welcome back to the second video for TEC 293 on Tuesday, March 30th. In the previous video, we did the heat treatment portion of Lab 7, and in this video, we're going to talk about how we're going to see and measure the effects of what we did in the heat treatment portion. Hopefully there are effects that we can see. Believe me, there will be. There'll be definitely noticeable effects of the heat treatment that we did. So I think I'm going to do several things in this video. First of all, I'm going to start by talking about impact testing. So we'll do that by sharing my slides and talking through a few things about impact testing. And then I think I'll go down to the Woods lab. That's Turner Hall, room 169. That's where we actually have the Sharpie V-notch testing machine. So I think I'll go down there and give you a little orientation to the machine so that when you come into the lab to do the second half of Lab 7, that's not the very first time that you've ever seen that machine. At least you will have seen it in this video today. So I'll step you through the process of doing an impact testing analysis on the Sharpie V-notch testing machine. And to do that, I'll take my computer and camera and I'll go down to the lab and I'll show you the machine and what you're going to do in the second half of Lab 7. And then the last thing I'll do in this video, we will look in the lab manual at Lab 7 and we'll talk through the steps that you'll do in the second half of Lab 7 as you test the specimens that we just applied a heat treatment to. So that's what we'll do in this video. So I'll get started by sharing my slides and we'll talk through impact testing. All right, in the previous class session, we talked about different modes of failure. We talked about ductile failure and brittle failure. And we said that the type of failure that will actually occur in real life is whichever failure mode requires less energy to occur. So if it takes less energy for a specific part in a certain set of test conditions to cause plastic deformation and necking, then you're going to get a ductile failure. If it takes less energy in a certain set of circumstances to cause crack propagation, then you're going to get brittle failure. And the way we quantify the amount of energy that a part can absorb before it fails is called impact toughness testing. And this is really important to quantify the toughness of a material. This is generally the test that people do to quantify the toughness of a material. You can also talk about toughness of a specimen under tensile testing and toughness of a testing under compression testing. We talked about that. That's the area under the stress strain curve, right? It's true, but generally speaking, when people talk about the toughness of a material, the test to determine the toughness of the material is the impact toughness test that we're doing in this lab right here. So we know that impact toughness is in general is the amount of energy that a specimen absorbs before it fails. So impact toughness is the amount of energy that absorbs before it fails due to impact. So we're going to cause an impact to occur to this specimen, and we're going to measure how much energy it absorbs when or as it's failing. There's two main different kinds of tests that you can do to do impact toughness testing. One of them is called Sharpie, not Charpie, but it's called Sharpie V-notch test. And the other is called the IZOD V-notch test. And they're really quite similar. The main difference between these two tests, well, I'll show you a picture in the next slide, but it's mainly just in how the specimen is held during the test, how it's supported during the test. Both of these are pretty old, about a century old, and maybe not quite a century old, but they were developed in response to some of the problems that people were having in the early 1900s. Like we talked about last time with the Navy and the problem with their Liberty ships, how they were just kind of spontaneously breaking apart and fracturing due to cold temperatures. And so this test was developed to measure the toughness of the specimens so that we can make sure that we are using materials that are not going to fail via brittle failure. Generally speaking, we prefer materials, if they're going to fail, you'd prefer a ductile failure because there's more warning. You know, you can see that something is deforming plastically, or you can see when it's necking, and you have usually at least some warning. It may not be real long, but it's more than if you have brittle failure. If brittle failure occurs, there is next to no warning. It's just the crack propagates and boom, it's over. So this is a way to measure the toughness so that we can get an idea of the toughness of the materials that we're building stuff with. All right, here's the difference between the two tests. It's mainly in the way the specimen is supported. So here I've got a specimen with the IZOD test. That's this one over here. You're holding the specimen vertically, and the notch is right here. I don't know if you can see the notch there. The notch is right there. So we're holding the specimen vertically like this. Here's the notch. And then the pendulum is going to come down like this and hit the specimen on the same side as the notch. And it's going to break off this top section of the specimen because we're holding the bottom of the specimen by the machine. All right, so the pendulum comes down like this, impacts the specimen, and breaks the specimen. And we're going to measure the amount of energy that is absorbed by the specimen as that pendulum comes through and breaks the specimen. We'll talk more about how we do that with the pendulum in just a couple of minutes. So that's the IZOD testing. Here is the Sharpie V-notch test. It's a very similar specimen, but we're going to hold it a little bit differently. It's going to be supported. Okay, there is the notch, and the pendulum is going to come in from the backside like this and hit it like this. So it hits it opposite the notch. It hits it right here on the backside, opposite from the notch. The pendulum comes down like that and hits it. All right, or to put it more in the perspective that you're looking at on the slide, here's the notch on this side, and the pendulum comes down like this and hits it right behind the notch on the opposite side of the notch. A little bit of foreshadowing here. The next unit, after we talk about heat treatment and after we do lab 7, the next unit is on beam bending. It's on, here's a beam, and we apply a force to it and we bend it. So we're going to talk about beam bending next. And the reason I bring that up now is because the way we support these different test specimens, we have a different name for it. So in the IZOD test, we call this a cantilever. This beam right here is supported as a cantilever beam. It's supported on one side and the other side is not supported. So that's a cantilever. The other side, the other specimen, the Sharpie specimen, is called a simply supported beam, which just means it's supported on each side of the beam. So it's supported on both sides of the beam like this, and then the pendulum is going to come in like this and it's going to break it. So the Sharpie V-notch specimen is a simply supported beam. That's just a little bit of foreshadowing to a week or so from now. All right, so we got this pendulum that's going to come down. It's going to impact and probably break the specimen. And then there's a dial up here at the top of the pendulum that we're going to read. And that's going to tell us how much energy the part absorbed as the pendulum swung down and through the specimen as it broke the specimen. All right, I just said this. All right, so the IZOD test, it's held vertically. The lower half is stationary and the notch is facing toward the pendulum, and the pendulum strikes the notch right here, and it's going to cause the specimen to break, and we're going to measure how much energy it absorbs as it breaks. The Sharpie is held differently like this as a simply supported beam with the notch facing away from where the pendulum is going to come down and hit the specimen. And once again, we're going to read the dial up here, the scale, and we're going to read that to measure how much energy the part absorbed as it broke. So what I'm going to do now is I'm going to go down to Turner 169. That's the Woods Lab on the north side of the building. And I'm going to show you what the Sharpie V-notch impact testing equipment looks like so that you'll be prepared to use it in the second half of this lab. I'm in the Woods Lab now in Turner 169. It's on the north side of the building. And back in the corner of the Woods Lab, we have our Sharpie V-notch impact testing machine. This is a pretty old machine. In fact, on the back of the machine back here, there's an ID tag that shows that it was owned by the US Army at some point. So this has probably been around for a long time. My guess is it was probably used by the armory in Joliet, around Joliet at some point, but they gave it to us, or we purchased it at some point from them, way before my time. And this is also a relatively dangerous piece of equipment. It would be pretty easy to lose a finger if you're not careful with what you're doing. If you're messing around down here, installing a specimen, and this pendulum swings down, it would be pretty easy to at least break, if not lose a finger. So you got to be real careful with this. I'll be right here, but let me know if you have any questions. It's not difficult. You just want to make sure you're paying attention to what you're doing. All right. So it consists of a pendulum. This pendulum weighs about 90 pounds. So it's heavier than it looks. You know, I make this look easy because, you know, I'm so massive and strong, but it's actually pretty heavy. And to lift it up, it takes a fair amount of force to lift it up. Basically, what's going to happen is we're going to lift it up. And it actually has a catch here. It has a catch right there. And basically what we're going to do is we're going to trip the pendulum by pushing this lever right here. Push it back towards the wall. And after I do that, it's going to release the pendulum. The pendulum's going to swing down. And if there's a specimen down there at the bottom, then it's going to break that specimen. Once it breaks the specimen, we're going to read this needle, this movable needle on this scale right here. And I'll show you how to do that. All right, so the order that we're going to do this in, I'm just going to release it first. Slowly lower it down. All right, the order that you're going to do this, when you first get ready to do this test, the first thing that you want to do is do a reference test. It's kind of like calibrating the machine, because if you think about it, if we let this swing with no specimen in there, it should read 0. Right? It should read 0 foot-pounds is the unit we're going to use. It should read 0 foot-pounds because there was nothing down there to break. It won't always read exactly 0 foot-pounds because there's a little bit of play in the machine. It's not perfectly calibrated. So to do that, the first thing you're going to do is actually run the test without a specimen in there at all. So this is the first thing every group is going to do. You're going to bring this up to its upper position, and then this is really important for every single test, especially the ones where you have a specimen in there. It's really important to make sure that you move the needle to the left. All right, if you don't do that and you have a specimen in there and you run the test and you didn't reset the needle, you might not get any data on that, and then you're out of luck because you only have one of each specimen. So make sure you remember, and everyone in your group, remind each other before each test, make sure you zero out the needle by moving that needle to the far left position. All right, so we're still in our calibration of the equipment. The first thing we're going to do is run a test without a specimen. I'm going to go ahead and trip this, make sure everyone's standing clear, yell, clear. All right, now we've run the test, and we're going to read that needle in just a second. But first, I'm going to stop that from swinging. The best way and safest way to stop it from swinging is to apply the brake. There is a brake in here, and it's kind of loud. So prepare for a loud creaking noise. It's pretty unpleasant, but that's the quickest way to stop it. To engage the brake, you push in on this button right here. To disengage it, you pull the button out. But it's a gear mechanism inside there with the brake. And so sometimes to disengage the brake, you have to pull up on the pendulum and pull out on the brake button at the same time. All right, so now we've run that first test. Now we're going to read the dial right here. And this is actually, you'll see it, so I'm not going to bring the camera up here, but this is actually pretty close. I'd say it's about one foot-pound.
So when we ran the test without a specimen in there, we got 1 foot-pound. It should be 0, logically. So what you're going to have to do is, if you were running this test right now, from each reading that you get with the specimens, you're going to subtract this value. So in the next test you run, if you get 30 foot-pounds, you're going to subtract this calibration value of, in this case, 1 foot-pound. So your actual value for that test would be the 30 foot-pounds minus the 1, so 29 foot-pounds. All right. You're going to have to do that subtraction for every single specimen, but you only have to do this calibration once at the beginning of your lab. But I want each lab group to do it. Okay. All right. So we've got the calibration out of the way, if you will. Now we're ready to actually start testing a specimen. I don't have any specimens on me right now, but I'll step through the process. What you want to do first is lift the pendulum up just a little bit and engage the brake. It's much safer to install the specimen with the pendulum here than it is if the pendulum is all the way up. That's a good way to lose a finger if somebody were to bump the lever or the brake were to fail. But the pendulum just a little bit raised up like this. Now I take my specimen and put it in the holder. I know you can't really see it, but you will. And you're going to put the specimen in here. It needs to be centered in here, and the notch needs to be facing to the left. Right? Centered, notch to the left. Okay, once the specimen is in there, then you can raise the pendulum all the way up. Disengage the brake. Raise it all the way up. Now remember, what do we have to do for every single test? Always move the needle back so that you can get good data on this. As the pendulum is going to swing, it's going to move that needle, and we want to make sure that it's relevant to this specimen. All right, so now we're pretending like we got a specimen in there. We've zeroed the needle. We've got the pendulum up. And now we make sure everyone is clear. I'm kind of joking, but you can yell clear if you want to. Yell clear, and then push the lever back. And now to stop it from swinging, we can engage the brake. Oh, that is very unpleasant. And now, of course, the part, if it had failed, it would be flying this way. So we find the specimen on the floor, and you want to look at it so you can tell if it failed, either nozzle failure or brittle failure. And you want to read the dial right here. So it's going to be on the upper side of the dial. I know you can't see this, but there's a 20, 40, 60, 80, and so on and so forth. And those units are in foot-pounds. Foot-pounds is a unit of energy. It's also a unit of torque. But in this instance, it's being used as a unit of energy. Basically, if you have a 1 pound mass object, and let's say you have it 1 foot off the ground, you have 1 foot-pound of potential energy. Right? That's the context it's being used in here. All right. So read this value after the specimen fails. Don't forget to subtract your calibration value that you measured at first. And then find the specimen. You're going to have to take pictures of the specimen for inclusion in your lab report and calculate the toughness measured in foot-pounds. And then you'll repeat this for all 6 of the specimens, including the one that's in liquid nitrogen. So we'll have a bucket of liquid nitrogen over here, and you'll use the mitts and the tongs to grab one of those specimens out of there. And then it's a little bit tricky. It is a little bit tricky, but you'll use those tongs to install the specimen that has been in liquid nitrogen into a holder over here. All right, so that's a quick run through. I think that's better than just reading through the list of steps. So I wanted to make sure that you get a sense of what it's going to look like when you do the impact testing.
Here's a closer look at the dial gauge portion of the Sharpie V-Notch impact tester. So now you can see the scale. So it starts at 0, it goes by 1, it counts by 1 up to 10, 20, 30, 40, 50, 60, etc. So after each test, you're going to read where this needle is right here. So right here, if we had just done a test, it looks like this needle stopped at a little more than 140. It's a little bit hard to see in this picture, but that looks like it's probably just over 140, 141, 142 foot-pounds, something like that. Remember that you're going to have to subtract the reference value that you got with the first test without a specimen from that value. All right, so what do we got? Here's the gauge with the numbers. This is the needle that you're going to read the gauge from. This is the part that is attached. It's fixed, attached to the pendulum, so that when the pendulum swings, it moves this as well, which moves the needle. So as it swings over, it moves the needle over like that. So it kind of makes sense. The farther the pendulum swings, the farther over the needle is going to go, which means the less energy that was absorbed by the part as it failed, right? If the pendulum got to the bottom and it stops, like it didn't break, like if the specimen didn't break, then it would be way over here. It would be some number over here. And then what could you say? Think about this. What could you say if you have the needle, say, right here, but the specimen didn't break? Well, toughness testing is supposed to measure the amount of energy required to cause a specimen to break. So what's the best thing that you can say if you're reading the dial and it didn't break? Well, you can still read the dial. Let's say the needle was right here and the specimen didn't break. You can say that it's greater than, the toughness is greater than whatever this reading, excuse me, whatever this reading is right here. So if you get a specimen that doesn't break, you should say that the toughness was greater than whatever the reading was, and still subtract your reference value that you got initially, okay? All right, this is the pendulum down there. This is the brake button. You push to engage the brake, and you pull to disengage the brake. And the trip lever, you can barely see it, but it's over here. To release the brake lever, you push towards the wall, and to engage the brake, to engage the trip lever, all you have to do is lift the pendulum up and it will automatically engage with the trip lever. All right, so here's the procedure. I just kind of went through this. I talked through it in the lab. So you got to wear eye protection. We have to wear masks this semester. Keep clear of the machine because it can do some damage. It's a heavy pendulum. It can do some damage. So the first couple of steps are to get that reference value, because you know that when you do a test without a specimen in there, it should be 0. I mean, it makes sense that it should be 0. So if it's not, then you have to subtract that reference value from any subsequent test that you do. So the first thing you go ahead and do is this reference part. So raise it up to the upper position of the pendulum, engage the lock. It'll engage automatically when you lift it up. 0 the scale, that means the needle, move it all the way to the left. And then without a specimen, go ahead and trip the pendulum by pushing that trip lever back, and then allow the pendulum to swing and read the value on the scale. That's the reference value. And you're going to subtract that value from all the other data that you get in the lab. Okay, now you're done with the reference, or the calibration of sorts. Now you can go ahead and do testing on the specimens. So to do that, take the pendulum and move it to an intermediate position just to the right and engage the brake. And then you can go ahead and install the test specimen. It should be centered and it should have the notch facing away to the left from the pendulum. And once that's centered and installed in there correctly, then you can raise the pendulum. You have to disengage the brake, but then raise the pendulum all the way up to its upper position. Make sure you 0 the scale. Usually when we do this lab, there's at least one group that forgets to 0 the scale. And so we have to figure out what, some other alternative arrangement. So please remember to 0 the scale by moving the needle to the left before each test. Now you're ready to do the tests. So everyone staying clear, trip the pendulum lever and allow it to swing. And then you can go ahead and stop the pendulum from swinging by engaging the brake, and then read the needle on the gauge. And that's the amount of energy measured in foot-pounds. From that value, you need to subtract the reference value. So take the reading that you get with the specimen, subtract the reference value. That's the toughness. That's the Sharpie impact toughness of that specimen, measured in foot-pounds. And then you repeat just these last 4 steps, 4 through 8. I guess that's 5 steps. Repeat that for as many specimens as you have. All right, what I'm going to do now is switch over to the lab manual, and we've talked through a lot of this, so I won't have to go through the procedure in great detail, but I want to talk through some of the discussion questions and things on Lab 7. So I'm going to flip over to the document cam, and we'll talk through the rest of Lab 7. Okay, here's the second half of Lab 7. It starts on page 77 in your lab manual. I've already talked through this actually kind of twice now, once down in the Woods lab and once by going through the steps in the PowerPoint. So this is the same thing. It's important that you read through this and understand the order in which you're going to do this. Otherwise, you might miss out on some data. So make sure that you understand how to do this procedure, but I'm not going to belabor it anymore. So one thing I will point out is I want you to make sure you take a picture of each specimen after the testing is over. You're going to use that to answer some questions in the lab report. And I'm also going to go over this. You should save your test specimens in case you want to do some extra credit. There is an extra credit opportunity at, I'll discuss that at the end of this lab. All right, so for the results, what you need to do is calculate the toughness. You're just subtracting these values like I've mentioned a couple of times. You're going to calculate the toughness measured in foot-pounds, show your calculations. You need to make a table of all the data that you collected as well as the toughness for each specimen. And you could also measure the toughness in a different unit of energy that is more commonly used as a unit of energy. Joules is a pretty common unit of energy, whereas foot-pounds, most people don't even recognize that it is a form of energy. So you can convert into joules, and I want you to do that using this conversion factor, and make a table showing the impact toughness in joules. Then to display the data, I want you to make a bar graph showing the impact toughness. You can show it either in joules or foot-pounds, either one is fine. The vertical axis should be the toughness, and the bars should be along the horizontal axis. So something kind of like this, where this is the toughness. I'm not going to write that out. Toughness in foot-pounds, and this would be the specimens. So your bars are like this, something like that. 1 bar for each specimen. And when you label these, each one of these should have a label. Make sure you label them or with a legend or something. Make it clear. Sorry, you couldn't see all that graph there. So make it clear which specimen heat treatment corresponded to which bar, because I don't remember which one is specimen 1, and you won't either after a week or maybe even less than that. So make it some way with a legend, or put it on the label down here. Write down what kind of heat treatment was applied here and what kind of heat treatment was applied here, or include it in a legend or something. Don't just label it specimen 1, specimen 2, specimen 3. All right, that's not nearly as informative. And then I want you to insert the photos showing each of the specimens. Get a good picture. I mean, your phone is fine. Just use your phone and try to get kind of a close-up showing the way that each specimen failed. When you put them in your report, label them. Make sure you tell me which specimen it is and which heat treatment process was applied to each of those pictures. Then we get into the discussion questions. The first question is, based on all of your results, including the appearance of how they looked, which specimens were brittle, and how do you know they were brittle? Refer to everything that you collected in the lab, all of your data, your tables, and your pictures. The second one says, based on all of that, all of your results and all your data, which ones would you categorize as ductile? The third one is very similar. Based on all of your data and results and pictures, which ones would you categorize as tough? You can answer more than one for all of these. I'm not asking you which one is the most brittle or the most ductile or the most tough. I'm just asking you which ones, one or ones, were brittle, which one or ones were ductile, which one or ones were tough, and why. Make sure you explain in each of those cases. Number 4 is where I want you to explain your results. So you now know quite a bit about heat treatment and toughness and different types of failure. So tell me about the results and tell me why you got those results that you did. You should refer to the crystalline structure, what happened to the crystalline structure of the steel during that hardening process. You should refer to some forms like martensite and bainite, if applicable, and ferrite and perlite, if applicable. Talk about what happened to the structure of the steel during the tempering process and during the annealing process. And talk about why the specimen that was cooled in liquid nitrogen, why did it do what it did? All right, so how do these effects correspond to your results? And make sure you use the terminology that we have been discussing for the past week in class. All right, that's the end of the lab report. There is an opportunity for extra credit. If you want to do the extra credit, then talk with your group, because I would like you to come in as a group. That way it saves me some time, frankly. I don't want to have to schedule 20 or 24 different people coming in for this. So anybody in your group that is interested in doing this, then talk amongst yourselves and then get with me and we'll figure out a time that you can do this in the next week. So this is due at the same time that your lab report is due. All right, and you can do this if you want to. Let me know ahead of time, but I think I should be available right after the lab if you are interested in doing it right after lab 7. Basically what this is measuring the hardness of each of these specimens, except specimen 6, because that one had liquid nitrogen, and we're not going to have liquid nitrogen when you do this. So specimens 1 through 5 measure the hardness using the Rockwell B scale. So we'll go down to the lab with the Instron machine in it, and you will do hardness testing with the Rockwell B scale for each of those 5 specimens. So let me know if you're interested to do this. You can get up to a maximum of 5 points of extra credit on your lab report. So you could get potentially up to a maximum of 15 out of 10 on lab 7. When you do this, you need to make sure you do the test 3 times for each specimen. That's the standard ASTM procedure. Once you do this, make a table of all your data. Make a table for the average hardness value for each specimen, and then create a bar graph showing the average hardness value for each specimen. And then importantly, make sure you describe and summarize your results, including why. Why did you get the results that you did? So describe which ones were hardest, which ones were the softest, and then explain why that was. Why were some of them harder than others? Make sure you use the knowledge that you've gained, hopefully, in the last week. Use the proper terminology. Talk about the difference in the grain structures between the different specimens as we did different heat treatment processes to them. And just make sure you explain what happened to each of the specimens to cause it to have the hardness value that it did. All right, that's going to wrap up our discussion of impact testing and of the instructions for the second half of Lab 7. I think this is going to be a lot of fun. I'm really looking forward to it. I hope you are too. One last reminder, if you want to bring something to the lab to freeze in the liquid nitrogen after we're done with all of the Lab 7, work that we're going to do. You can bring something if you want to see what happens when you get it really, really, really cold, like negative 200 and something degrees Fahrenheit cold. You can. I've got it on my calendar to bring a bag of marshmallows. So I'm going to bring some marshmallows so that we can freeze them and then eat them. And it's just kind of a weird experience to eat frozen marshmallows that are really, really cold. But it's pretty cool and it's pretty fun. And so if you want to bring something, as long as it's not super destructive or is going to make an enormous mess, then that's fine. We may as well take advantage of having that extra liquid nitrogen. As long as it's a nice day, probably what we'll do is we'll take it outside on the north side of the building on Turner Hall, and we'll play around with the liquid nitrogen, and that way it's okay if we make a little bit of a mess. The only thing I really would ask is that if you're going to bring something, if you're going to play around with the liquid nitrogen with us, then please help to clean up whatever mess we end up making. It probably won't be too bad, but we'll just bring a couple of brooms and dustpans out there, and we'll just clean things up a little bit after we're done. But that won't take very long. So anyway, that's about it. I'm looking forward to it, and I'll see you in Turner 169. That's the Woods Lab. I'll see you for the second half of Lab 7.